This is Mr. Barron. I'm going to show you how to solve a problem from the 2009 AP Chemistry test. This is problem number 1, which is an equilibrium question. When you look at the question, it says use the information below to answer part A1. Part 1 is asking which of the two acids is stronger, this one or this one. Well, the first thing you should do is you should notice that you have something called Ka available to you. Ka tells you how much the acid actually dissociates. It's your acid dissociation constant. The greater your acid dissociation constant, the stronger your acid. So which one's stronger? What I would say is HOCl. And the reasoning behind that is because the Ka value is actually higher. And remember, the Ka is your acid dissociation constant. So if you wanted to write it out, it would look like this. It would be H plus, so Cl minus, over the HOCl. Remember, it's always products over reactants, and that makes sense in terms of which one's stronger. The stronger acid is going to produce more H+, so naturally, the higher the Ka, the more you have these two products than you do the original reactant. All right, the second part. Part number 2 says draw the Lewis electron dot diagram for the acid you identified in part A. So the one we identified was HOCl, so I'm going to write it over here, HOCl. And in terms of valence electrons, there's 1 with hydrogen, there's 6 with oxygen, and there's 7. So you have a total of 14 valence electrons to populate this molecule. So what I'm going to do is connect the H, the O, the Cl, and I used up, out of that 14, 4 valence electrons. So out of that 14, I'm going to take away 4. So now I have a total of 10 valence electrons left. Populate on the outside first, so don't want to fill in any more on hydrogen, just want to keep hydrogen with a duet, not an octet. So I've got 10, so 2, 4, 6, 8, 10. And that's the correct Lewis dot structure for number 2. Next question. Next question is, hypoiodous acid has the formula HOI. Predict whether HOI is a stronger acid or a weaker acid than the acid you identified in part A1. So when I look at this table, notice that the HOCl has a higher Ka, so it is a stronger acid. Because this one's stronger, let's think about this. What do we know about these two? Well, chlorine is more electronegative than bromine. It turns out that for these types of acids with oxygen in there, the higher the electronegativity of the halogen in particular, the stronger the acid. Iodine is at the bottom of your periodic table. Because it's at the bottom of your periodic table, it has a low electronegativity. The lower the electronegativity, the lower the strength of the acid. And the higher the electronegativity for these oxyacids, the higher, or the stronger the acid. So the correct answer is, for this particular problem, and I'm actually going to use the language that is used by the College Board, they say that HOI is a weaker acid than HOCl because OH bond in HOI is stronger than OH bond in HOCl. The lower electronegativity, electron drawing ability, of iodine compared to that of chlorine results in electron density that is higher, hence a bond that is stronger between the hydrogen and the oxygen atoms in HOI compared with the electron density between hydrogen and oxygen atoms in HOCl. So all you had to say for credit, that was a big long explanation, is that stating that 1 point for predicting that HOI is the weaker acid than HOCl, and stating that iodine has a lower electronegativity and that chlorine has a higher electronegativity, particularly that the higher electronegativity in chlorine results in a stronger oxygen-hydrogen bond than in HOI. Alright, now, let's move on to number B, or letter B. Write the equation for the reaction that happens between hypochlorous acid and water. So for that, it would be HOCl, and because they're actually describing water, I would be careful and I would write out water in your equation. So plus H2O, and of course it's liquid, and then of course you have the dissociation of the hydrogen, so you have OCl minus and H3O plus. For these, when it asks you to write out an equation, be particular, make sure you have the states of matter there as well. And that would be the correct answer. Now, the College Board also accepts the Arrhenius definition. The Arrhenius definition, of course, would be HOCl, and of course that ionizes into H plus and OCl minus. And of course these two can be flipped. It doesn't make a difference. All right, now moving on to letter C. In letter C, we're actually looking at a reaction. And the reaction is when you have hypochlorite OCl minus, which is aqueous, reacting with water, which is liquid, and it produces HOCl, which is aqueous, and hydroxide, OH minus, which is aqueous. And the first part says write the equilibrium expression. So of course you ignore the water, and your equilibrium expression would be K, and let's look, is it Ka or Kb? Well, when I look at this, this is ripping off a hydrogen, so this is a base, so I'm doing Kb, because of course hydroxide is produced, and the correct answer would be concentration of HOCl times OH minus over concentration of OCl minus. And of course I'm not going to have water in there at all because it's a liquid. We only write these things for things that are aqueous, not things that are liquid or solid. Alright, moving on. Now the next part is to calculate the equilibrium constant. Well, conveniently, we've been given Ka specifically for HOCl in the previous problem. And that value is right here, which is 2.9 times 10 to the negative 8. So if I know that Ka for HOCl is 2.9 times 10 to the negative 8, what I need to do is figure out Kb for OCl minus. If I'm solving Kb for OCl minus, this here is the conjugate base to this acid. So I can take this Ka and change it into Kb using Kw equals Ka times Kb. Kw, of course, is a constant. Kw is always equal 1 times 10 to the negative 14. So what you do is you rearrange your equation to solve for Kb. Divide by Ka on both sides. When you do that, you have Kb equal to 1 times 10 to the negative 14 divided by 2.9 times 10 to the 8th. And that should give you your Kb. The Kb in this problem, once you've done that calculation, and by the way, I actually did write something down wrong, and it's always important to double check your work. This doesn't make sense to have a concentration that large. I'm catching that because notice when I copied this down from the first problem, it's negative 8, not positive 8. And besides, positive 8 doesn't make any sense. Your answer would be totally wrong if you plugged in that 8. So double check your numbers on all of these problems. So when you divide these two numbers together, you get 3.4 times 10 to the negative 7, and that's your correct answer for Kb. Alright, now the last part of the question is actually asking you to calculate the value of hydroxide, and it gives you a particular concentration starting with sodium hypochlorite. So what they tell you is that you have 1.2 molarity of NaOCl. Immediately identify, looking at the formula, we know that the sodium in particular is going to be our spectator ion. Because it's going to be our spectator ion, we know that if we have 1.2 molarity of sodium hypochlorite, it's just going to give us 1.2 molarity hypochlorite. So what we're going to do is we're going to revisit the equation with hypochlorite and water producing HOCl and OH minus. So this is an ice table problem. The reason I know it's an ice table problem is because the question is asking for the concentration of hydroxide at the end. So we want to know how much we produce of this at the end. The given information, of course, is we just calculated Kb. Kb is 3.4 times 10 to the negative 7th. And I do know the starting concentration of hypochlorite, which we just did, which is 1.2 molarity. So this is my ICE. I know that I'm going to ignore water because it is the liquid one. Everything else is aqueous. This here is going to start at 0. This is going to start at 0. It's going to go down by x. This is going to go up by x, because the ratio is 1 to 1 to 1. If this was a 2, I'd have to put a 2 there. It's not, dealing with acids and bases here. So it's 1.2 molarity minus x. This is x. This is x. Alright, so let's write out the equilibrium expression with these x's substituted in for the reactants and products. So it'd be x times x, the product, so it'd be x squared over 1.2 minus x. And I know my Kb, so my Kb is 3.4 times 10 to the negative 7th equals x squared over 1.2 minus x. And if we solve for x, then I know the concentration of hydroxide. So it's a quadratic. You could solve it as a quadratic, or you could know that x is going to be really small. And if x is really small, what you can do is you can look at this and go, well, we're going to assume it's 0 because it's really small, and 1.2 minus a small number shouldn't make that much of a difference. So it ends up being 3.4 times 10 to the negative 7th equals x squared over 1.2. Then what you have to do is you multiply these two, take the square root of both sides to solve for x, and x, which is your concentration of hydroxide in this problem, ends up being, oops, that's way too many lines for an equal sign. This would be 6.4 times 10 to the negative 4th, and please make sure you label it with the unit. Remember, your K's, your acid dissociation constants, and your base dissociation constants. This you don't have units, but once you eventually solve for a concentration, please label it as molarity. If you have any other questions, please let me know.